Hey guys, in this video we're going to have a look at how we can fine-tune YOLO version 5 using our custom dataset and see how well does it perform on some images that we have in our test set. Let's get started. YOLO stands for You Only Look Once, and the most current or latest version is known as YOLO version 5. Note that there is a huge controversy going on right now about the naming of this project, and there is a post on Hacker News that at least the first comment right here says that this is just bullshit, and there is a lot of accusations about calling out the authors of YOLO or the author of YOLO version 5. And yeah, I'm not going to spend any more time on this issue, but just be warned that this is something ongoing, and this video is going to focus on this repo, which is done by Ultralytics YOLO version 5. So we're going to have a look at that one. YOLO version 5 is completely written in PyTorch, and in my opinion, this project is very well done. This implementation is heavily based on YOLO version 3 and the experience that the guys at Ultralytics have using YOLO version 3. At least this is somewhat what they say. And this model appears to be very efficient and very well performant, at least compared among the YOLO implementations. Of course, you can see here that efficient.dat, which is a project or a model introduced by Google, is more or better at this task. And the task that we're talking about right here is real-time object detection. And I'm going to have a look at the leaderboards right there in a minute. And you can see that the authors acknowledge that in the future they might include updates using even some of the features which are presented in YOLO version 4. YOLO version 4 was introduced in the paper YOLO v4 Optimal Speed and Accuracy for Object Detection. Of course, this paper is available on arXiv, and the paper, or at least this version, is available as April 23rd. So you can see that right here we have a similar chart comparing the MS Coco, the performance on YOLO version 4 as compared to the efficient.dat on the MS Coco object detection validation set. And you can see, at least here in this chart, that the YOLO version 4 gets an AP of around 44, while the YOLO version 5, at least the largest model, gets around 47, 48, I would say. So at least from this very bare-bone comparison, we see that YOLO version 5 might be performing better. So this paper introduced a lot of cool new stuff. I mean, like cool new features and cool new ways to speed up YOLO version 3. And here we are seeing a chart or an image that is available in this paper. And this is the main difference between a one-stage detector and two-stage detector. All of the YOLO implementations are known as one-stage detectors. So they basically get some input, they have some backbone network, and then they produce those dense predictions. And the purpose of all of this is to have something that is very fast and runs in real time. So what this means is like something maybe 30 or even 60 plus frames per second. So YOLO are very good at those tasks. And if you want more accuracy, if you don't care that much about the speed or the speed of the inference of your model, then you might want to use something like RetinaNet or faster RNN or faster RCNN or something like that. When you use those, you have a second stage, which is essentially a quasifier, which states or which says that those bunch of predictions that we have from the first stage of the detection from something like YOLO, then you have an additional stage, and this quasifier right here gets the prediction or the dense predictions and classifies each one as whether or not how believable or how probable this prediction really is. So yeah, of course, two-stage detectors are are more performant, but they're slower, and there is a trade-off depending on the task that you want to handle. Finally, we are going to have a look at the leaderboards provided by the papers with code, which are, of course, bought by Facebook Research. So on the real-time object detection on Coco, at least this task defined right here, you can see that efficient det, which the largest amount of parameters, is performing very, very well compared to the YOLO v4. But the frame rates, and I believe that this is done on Tesla Visto, I'm not really sure about that, but we have around 9 frames per second with the efficient det, which is very poor. But with YOLO version 4, we have 62 frames. And at least in the Hacker News, we have a post right here by some guy or girl, I'm not sure, and we have at least this breakdown, which states that YOLO version 5 is much smaller, it's much faster, and is right about there on the accuracy. So you might expect that, of course this again can be controversial, but you might expect that you get a similar accuracy right here, but much faster performance or inference speed using YOLO version 5. So in the next video, we are going to try out YOLO version 5 maybe on a mobile device and see how well does it perform in the real world. Finally, we are going to compare YOLO version 4 with the state-of-the-art object detectors, which are not that interested in how well the accuracy goes. So here we have a leaderboard again on papers with code, and you can see that this detector S or something like that, which was introduced during this year, and it has the best results on object detection, again using the Coco test set. And if you look at this result, we have almost 55 of box AP. So if we go, and this stands for average precision AP, yeah. If you look for YOLO version 4, which is the first result right here, we have 43.5. So this is a very, very low result, at least compared to the first model. And you can see that the leaderboard position is very low as well. All right, it is time to start coding, and I'll open up a Google Colab notebook, and right here I'm going to start with checking the current GPU that we have for this machine, and we have a Tesla P100 with 17 gigabytes of VRAM. And right here I'm going to install the 3 command line tool, and then I'm going to copy and paste some of the requirements for the YOLO version 5. And right here you can see that I'm installing PyTorch 1.51, which is currently the latest release, which contains some very important bug fixes. And I'm installing also the Torch version 0.61. We are fixing or specifying the version of NumPy, which is required by the YOLO version 5 project. We are going to also use pyaml for some configuration files, and then I'm installing the Coco API, which is again required by the YOLO version 5 project. And if I run this will go ahead and start downloading everything. After the installation is complete, we are required to restart the runtime, so I'm going to do that. And I'm going to install the final dependency, which is going to be a project known as Apex, which is provided by NVIDIA. So I'm going to paste in the command right here and run it. So what this does is roughly clone the repo and starting the installation project. And what is this thing called Apex? So this is a recommended installation from the author of YOLO version 5. And this is a PyTorch extension which is used for mixed precision computations. So YOLO version 5 can be trained using more than one GPUs, and I guess they're using this mixed precision, so they might be using FP16 or FP32, so different floating point precisions, and this project speeds up the computations when you're using those kind of computations. So this is a nice additional benefit when you're training YOLO version 5 at least. Now that the installation of Apex is complete, we are going to rerun basically the whole code that we've used to generate the dataset, and I'm going to run all of the cells below this one. So this will set up some imports, download the JSON file, then we'll see the example image right here. And next we are going to execute our create dataset function for both the training and the validation set. And then we're going to see the examples right here for at least one of the annotations. The one thing that I did right here compared to the last video is that I've gotten the categories, converted them to a list, and then I've sorted them so we have reproducible class names right here, which is going to be important at least when we are training our YOLO model. So the dataset creation is now complete, and I'm going to start the fine-tuning of the YOLO version 5. I'm going to go to the GitHub repo and get the clone URL, copy that one. Then I'm going to git clone the repo right here. All right, and then I'm going to check that the repo is indeed here. So here it is. All right, so next, just for the purposes of reproducibility, I'm going to enter the directory YOLO v5, and then I'm going to check out a specific commit that I've tested the project with. This might change into the blog post that I'm going to write, and this might be a bit further if there are some bugs that need to be fixed in the current implementation. So next, I'm going to go to the repo once more and have a look at the type of models that we have right here. So we have a pre-trained checkpoints for YOLO v5 SMLX and SPP. So for our purposes, I'm going to take the best performing model, which is of course the slowest, but it has the largest amount of parameters. And I expect that this will indeed give us somewhat good performance. At least in our case, we are not that interested in a real-time object detection, while you might be, and you will have to take that into consideration depending on your hardware and the accuracy that you want to achieve. So for this purpose, I'm going to show you how you can create a specification for your dataset, and then we are going to download or create a configuration file for the model that we're going to use. So both of those files are stored in Google Drive, and I'm going to show you their contents right now. So I'm going to download the two files. I'm going to copy and paste the commands. So we are in the YOLO version 5 directory, and you can see that we are downloading datacoding.yaml and YOLO version 5x, which is again the largest model. So those files will be stored right here into data coding YAML. So let me show you the contents of this coding.yaml file. So here we have a path to the training set, and this, if you recall from the last video, is into this directory coding. So the structure right here says that the dataset should be outside of the YOLO version 5 directory. And we have the training and the validation set. And if you recall right here, we have the images and the labels. So both of those are training and validations. We have NC, which stands for number of classes, and we have 9 classes. And this one is really important. The class names should be the same as those that we printed out right here for all of the categories that we have. Because you just want them to match. So this is why the sorting right here was required. All right, so what about the next file, which is this YOLO version 5x? So let's go and check it. And I'm going to download this as well. Open it and show you the config for this one. So essentially the only thing that I've changed right here compared to the default file was this, again, the number of classes that we have right here. So again, we have 9, and this is a specification of the backbone and the anchors, which are the initial positions at which the bounding boxes should be looked for. So this is pretty much unchanged, and the same thing that is going on with the current implementation. So now that we have an understanding of those files, we can continue. And next we are going to basically follow the guide, which says that if you want to train the YOLO model, you have to run this train.py file and pass it some configs. So I'm going to do just that. I'm going to call the file, and I'm going to specify the maximum image width of this, which is going to be 640 pixels. I'm going to specify that each batch should contain 4 images. This is roughly how many can we fit into the memory of one P100. You might try 6, it might work as well, but I'm not risking some out of memory exceptions here. Then we are specifying the number of epochs, and I'm going to fine tune this for 30 epochs. I'm going to specify the config for the dataset, and this will say that we are going to use the coding dataset that we've I've shown you. Next, I'm going to specify the config of the model, which is again models YOLO v5x YAML. So this looks very good. And another thing that is very important to pass in right here is the weights. So I'm going to do the pre-training with YOLO v5x.pt, which is a pre-trained checkpoint for the PyTorch implementation of YOLO v5. And this will be automatically downloaded since this checkpoint is not available currently into the directory of our project. and I'm going to specify the name of the model. So I'm going to name it YOLO V5X underscore coding. And finally, I want to cache the images into the proper format for maybe later training, if you are inclined to do some fine tuning or hyperparameter tuning on that. So the model, the whole process has started, at least for now. And you can see that this is using CUDA Apex. So the actual Apex implementation is being used. And we have some of the hyperparameters that we are going to use for fine tuning our model. And you can see this is basically the whole architecture of the model. Another interesting thing right here is that this is actually starting TensorBoard for us, so the results will be loaded right there if you're interested into checking those out. And you can see that we are actually downloading the weights of the model. So YOLO v5x.pt, and this checkpoint is around, let's see, do we have the information for this one? I'm going to open the model and have a look at, yeah, YOLO v5x.pt. So it's roughly under 200 megabytes, at least that checkpoint. And next you see that we are training for 30 epochs. We are analyzing some anchors, which is basically a smart way to change those anchor values that we've seen into the model config file and fine tune them a bit for our dataset. So we have 453 images that we're going to use for training, and we have 51 examples or images for the validation. And you can see that we are using roughly 10 gigabytes, around 10 gigabytes of VRAM. Now that the training is finally complete, you can see that we are done in approximately 0.45 hours. So that's a bit strange. Anyway, so we've done 30 epochs, and you can see that the best and the worst weights were stored right here into the weights directory. So here you can get your fine-tuned model or the checkpoint for that with the best MAP, so probably mean average precision. So you can see that the final results are actually very good, at least on the 50 images that we've tested right here. Another thing that you can see into the project structure right here is that you have some images, and unfortunately on any of those I don't think that any predictions were done. And for example, you can have a look at some training batches. So you can see the annotations from some of the images, including, of course, some image augmentations that were done by the YOLO version 5. Next, I want to show you this image, which we are going to see in a minute. And this one takes the information from the directory called runs. And you can see that today we have, sorry, this is the runs for the TensorBoard actually. And the results were taken from this text file. So this is a summary of all of the metrics that were done during each epoch. So I'm going to show you a brief plot that is provided from these results. So from the utils, I'm going to import plot results, and I'm going to call the plot results function right here. So this should take into account the charting preferences that we had, and you can see that roughly we have recall that was very close to 1 at some point, but the precision was increasing up until the epoch 20. You can see that the classification was steadily decreasing, and overall the project was very well trained, and you might argue that you might benefit from training this model even for more epochs, for example 50 or more, or you might want to just go ahead and fine-tune the hyperparameters that were used. So this is not something that I'm going to do, at least for this video, but if you're working on some real-world project, I would suggest that this might be a viable next step. Of course, if you're using YOLO version 5. So next I'm going to create some images on which we are going to do some inference, and I'm going to select 50 images from the validation set. And I'm going to take just the first 50 and I'm going to copy those into inference images. So this is the folder right here. So we have 2 images already, and I'm going to copy some of the validation images right here. So inference, I made a typo. And again, I have an error. So quoting, oh, I should exit this directory. All right. So hit 50, yep. And this should copy the images right here. We have those. So from this directory, I'm going to run the detect.py file, and I'm going to pass in the weights that are best, that we find are doing the best during our training. And I'm going to specify that, again, I want the images to be in at max at 640 pixels. I want the predictions to be at least 40% confident, and I'm going to pass in the source, which is again inference images. So I guess this should be it, but let me just check again the command. Yeah, let's run this. So this should be relatively fast. The slowest part, I guess, is loading of the model, and after that you can see that the inferences are done sub 0.1 second. So if I open this and go to the output, let's open up an image right here. So you can see that for this, the model is drawing this bounding box, which is very good, and it predicts with accuracy of 46% that this is indeed correctly identified as genes. So let's open up another one. This should be trousers, I guess, which is again very good. Again, jeans, I guess. Yeah, the labels of the bounding box are not very well done in this project. So this is a jacket, so this is very good. And let's see that we have this image, which was not part of the dataset in any way. And you can see that at least one of the jackets were detected right here. So this is again on an image that the model haven't seen or haven't been fine-tuned on, because all of the images that we have right here are in this format. So I would say that this model performs much better than I've expected, because YOLO models are not very well known for their accuracy, but this does a very good job. So now you know how to fine-tune a YOLO version 5 model using your own custom dataset. And you can see that the output, or the best performing model, was stored as a checkpoint, which is available for download by you. So in the next video, I'm going to show you how you can use that checkpoint and load it on a mobile device, deploy it right there, and will build a very simple mobile app on which we are going to use our own custom model. So please make sure to watch the next video as well. Thanks for watching, guys. I'll see you in the next one. Please like, share, and subscribe. Bye bye.